Hi, let's talk about how you're going to go about doing this practice test for energy and chemical reactions. So first things first, this is the format the actual exam is. You'll notice the information given. This does not need to be memorized. Any further information, for example, like here, if a specific heat capacity is needed, it is given, does not need to be memorized. All right, let's begin. For the potential energy graphs, here's how it's done. You will draw an axis, no matter whether it's endo or exothermic. When it says label potential energy of the reactants and products, that means if it's exothermic, whatever energy the reactants start as, it has this activation energy here, so it increases, then it decreases as the reaction progresses, and then it ends. So potential energy of the reactants, the way you'd actually label it is here, potential energy of reactants, potential energy of reactants, and here you'd have potential energy of products. And then once you finish labeling that, we've got these two. Now the correct x-axis label would be time. And then the correct y-axis label would be potential energy. And then once you've got potential energy on there, the next one, show how the energy changes as the reaction progresses. That's actually what this line is. It shows how the energy initially increases as bonds are broken, which is always an endothermic process. And then the exothermic process of forming new bonds, this is the forming new bonds right here as energy is released. And since energy released is greater than energy absorbed, it's overall exothermic, and that's why this is correct. Make sure to have this clear activation energy, aka energy absorbed for breaking the bonds, as part of your graph. Now for the other graph showing an endothermic change, it's going to be the same kind of process, as in you're still going to need an axis, and you're still going to show potential energy for the reactants and the products. And this does correctly show how the energy changes as the reaction progresses. So it's just a matter of labeling them, such as there we have the potential energy of the potential energy of the reactants, and here we have the potential energy of the products. And then the correct x-axis label of time, as well as the correct y-axis label of potential energy. And this last one, of course, is addressed by the fact that the line goes like in this correct form. Sometimes people incorrectly like have just a straight line or something. You got to show the activation energy, this large hump shape right here. Okay, now having mentioned that, onward to the next question. So how to do this? First thing to look at is consider where you're going to do this, and because you see a temperature change, you know it's going to be Q equals MC delta T. And since this needs to be shown as part of the work, I'm going to stop rewriting that because it's going to be a necessary thing to figure it out. Again, because of this change in temperature. So, did the iron release or absorb energy? That actually can be answered immediately, nowhere needed, because all I got to do is look and see the fact that, oh, look, it's getting warmer. If it raises in temperature, then clearly it absorbed energy. If it had been getting colder, you would say released energy. So as far as how you're going to do this, the next thing to do is note that, okay, so Q is the energy in joules. So Q equals the mass, that's 1.3 grams, times specific heat capacity, given right here, 0.45 joules per gram degrees Celsius, times the delta T. Oh, what's the delta T? Well, delta T equals this. Now, do notice that when it comes to delta T, 46 minus 25 is 21. 25 minus 46 is 21, just with a negative sign. So it doesn't matter what order you subtract them in, but use your brain, because if it's warming up, make sure your delta T is positive. 3 Celsius minus 25 is 21.0 degrees Celsius. So if it's getting warmer, make sure it's a positive delta T. If it's getting colder, then make sure you have a negative delta T. So because it's getting warmer, positive delta T, 21.0 degrees Celsius. As a reminder, this does not count for your sig figs, however this does and this does, so I know it's going to be a 2 significant figure answer. Note that degrees Celsius cancels degrees Celsius, gram cancel gram to give joule as your uncanceled unit, and therefore your answer. So Q equals, and then we'll calculate that out, and that's the raw and rounded calculator answer that I get for it. So that is 12.285 joules, which we then round properly for significant figures, i.e. 12 joules, making sure it's a positive number because temperature went up, which means a positive number. Box that. Optionally, you can include the word absorbed in there because energy was absorbed. So that's how you handle that one. Now we'll look at another portion of this. So now we're on to the back side of the worksheet number 4. So when it comes to this, we got to consider what we're being asked for. So this metal is being allowed to cool, so we have a temperature change, and it gives you energy and asks what was the initial temperature of the copper. So we got to consider what are we going to use that involves energy and a change in temperature, and that tells me we know we're going to do a Q because MC delta T in here somewhere. So let's start with the fact that it is Q equals MC delta T. And then it says, okay, that's the equation. In order to determine the change in temperature, so that means we need to get delta T by itself. So that means divide by MC, divide by MC. Remember, you got to divide both sides in order to make sure that it cancels properly and you're being equal on both sides. So delta T equals Q over MC. So that's why it says variables only, no numbers. This is the answer. It does say show your work and box the final result. So that was the work. That's the rearranged number to determine the change in temperature. Now we're going to plug in the numbers and get the temperature change. We got a problem before we do though. Notice this is units of joule. This is units of kilojoule. This is units of kilogram. Kilogram is not the same as gram. Kilojoule is not the same as joule. We need to convert this and this in order to have units that play well with these, because remember we set up units first. So I'm going to get the kilojoules first. 400 kilojoules. You have to remember that kilo means 1,000, so 1 kilojoule is, you can put 10 to the third or the number 1,000, whatever you prefer, joules. And then the answer to that one, well, is 400,000 joules. So that's part of our answer. Well, that's part of the setup we need for the answer. We also need to know it's 1 kilogram. So 1.00 kilogram times 1 kilogram is 1,000 grams. And that's going to be, well, 1,000 grams. But with 3 sig figs, so we got to watch that for later. Well, we do have the joules, do have the grams. So what we're going to do is take this exactly as it is. So delta T equals Q over MC. Always write the equation you're going to use. Since we got it here, we can just repeat it here. We don't have to start from Q equals MC delta T again. Plug in the numbers. So Q is 400,000 joules. Mass is 1,000 grams. And then the specific heat capacity is this, 0.385 joules per gram degrees Celsius. Let me extend this to make it clear it's on the bottom. All right, that's the whole thing. And then we just do the calculation. And check out a way to do this calculation properly without making a mistake. You could take this and divide it by this in parentheses or do it one little piece at a time. Watch this though, 400,000 divided by 1,000. Push equals. And then this is also about divided by this too, divided by 0.385. It works. This is mathematically the same as if you like put these in parentheses and take this divided by that. So being that we got this now, here's the raw calculator answer. 1038.9611039 degrees Celsius. And another thing, delta T, let's back up a second. I should have said this before. If it released 400 kilojoules of energy, it should have been negative 400, which means negative 400,000 joules, which means negative 400,000 joules, which means a delta T of negative 1,038 and whatever. So because of that, the delta T, we're going to round for sig figs. Let's put it in scientific notation. How many sig figs? 3 sig figs. This came from a 3 sig fig number. This came from a 3 sig fig number. Round this is 3 sig figs. 1.04 times 10. Oops, just realized my bad. Negative 1.04 times 10 to the third degrees Celsius. So that's how you handle the delta T calculation. Now, what was the initial temperature of copper? All right, this is a use your brain kind of moment. It's not too hard. Look, it got colder. Its temperature dropped by over 1,000 degrees, which means originally it was, if it was over 1,000 degrees warmer than what it ended at. If it ends here, it was over 1,000 degrees warmer than that. So it started at around 100 degrees Celsius, and then what was the original temperature? Well, we'll use our rounded number, I suppose, and I guess we should do this properly. 100 degrees Celsius plus 1,040 degrees Celsius. It must have started out at 1,140 degrees Celsius. Technically, this is a 1 sig fig number, so underline that number, underline that one, round here. So round to the nearest 100, so that's, that would round to 1,100 degrees Celsius, i.e. 1.1 times 10 to the third degrees Celsius. I think we'll be forgiving when it comes to sig fig rounding when it comes to this particular one, but to follow the technical process, that's how you do it. And you would get that as the initial temperature, because it must have started a lot hotter than this and cooled down. And since we know how much it cooled down, it must have started 1,040 degrees warmer than it ended up. So that's the process there. Okay, next. What about how much energy in joules is released when you freeze 9.85 grams of water into ice at 0.0 degrees Celsius? Notice there's no temperature change. Just freezing it means you start at 0, where water is liquid but about to freeze, and end at 0, where it has successfully finished freezing. No temperature change. For that reason, we're going to use the number that came from here. More specifically, this one, the heat of fusion. We're going to use this. More specifically, though, how are we going to actually make it work? Well, that has a unit of, look, joules per gram. So use your units first, not your numbers. This is grams. So this is the units we've given, the heat of fusion and the units right here. Look, if you multiply them, you'll get joules, which is what it's asking for. So that tells you that it works. Okay, how many joules per gram? 334 joules per gram, according to the data table. Now, this is the amount absorbed when water ice is melting. Now, if it's freezing, it's releasing energy. So that means negative 334 joules per gram when it's freezing. And I think I said that wrong a second ago, sorry. Negative energy when it freezes because it's releasing energy. When it's melting, it absorbs energy, and that's a positive number. All right. What I do then is times by grams, 9.85 grams to be specific. Now I know gram cancels gram to give joule for the answer. So essentially saying take this number times this number. So negative 334 times 9.85 is that. Negative 3,289.9 joules. That's how much energy is released. So let's do that in scientific notation and round it properly for 3 sig figs, 3 sig figs. Better make this 3 sig figs. That will be negative 3.29 times 10 to the third joules. Or you could answer with an absolute value and say 3.29 times 10 to the third joules released. And that would get the job done. All right, now that being done, on to the next one. All right, let's try and straighten this paper up a little bit. Okay, there you go. A mass of metal is heated to 512.7 degrees before being dropped in 50 grams of water. This causes the water's temperature to rise from that to that. What is the specific heat capacity of the metal? Okay, this is the one where, yep, using Q equals mc delta T. It asked for what's the specific heat capacity of the metal, so I solve m delta T, divide by m delta T on both sides. M cancels M, delta T cancels delta T, cancels T, whatever. So C equals Q over M delta T. So the mass of the specific heat capacity of the metal is the mass of the metal, which is right here. Delta T of the metal, we can figure that out from this. And the Q, which is not given anywhere. So we're going to take advantage of the fact that Q of metal equals Q of water, because every joule released by the metal as it cools down is absorbed by the water. If you drop hot metal into water, the metal will release its energy, the water will absorb it. Therefore, metal has a negative Q because it's releasing energy. Water has a positive Q because it's absorbing the energy and warming up. Think about it. Metal gets cold when we put it into water because it loses energy. The water warms up when the hot metal is dropped in because it gained energy. So I'm going to take advantage of that by saying, well, let's find the Q of water. So Q of water equals mc delta T of water. So delta T water equals, let's see, it got warmer, so 24.8 degrees Celsius minus 20.4 degrees Celsius equals, that's 4.4 degrees, but I just want a 20.4 minus 24. Yeah, 4.4. Just making sure. 4.4 degrees Celsius is the delta T. So while I'm at it, let's do the temperature change for the metal too, because we're going to need that when we get to the metal. So delta T metal, the metal ended at the same temperature of water. The water rose to 24.8, the metal fell to 24.8. Equals 24.8 degrees Celsius minus, it started at 512.7 degrees Celsius. Ran off the edge of the paper there. Delta T of the metal, let's see, 512.7 degrees Celsius minus 24.8 is negative 487.9 degrees Celsius. That allows, now I've got the delta T for both water and metal. Okay, let's find Q for the water. So Q water equals the mass of 50 grams for the water, 50.0 grams for the water. As always, you just got to make sure if you're finding Q for water, all the numbers got to be for water. So mass of the water times the specific heat capacity of the water, which is given in your reference table right there. Oh, sorry, not there. Right there. 4.184 joules per gram degree Celsius times the delta T of the water, which is the 4.4 degrees Celsius. And the Q of water is going to be that much. So if that's the Q of water, then we're going to put that as 920.48 joules, which means if the Q of metal is opposite of Q of water, Q metal is equal to negative 920.48 joules. You might ask, wait, why didn't you round that off? The answer is because it's not my final answer. Round at the end. All right, final answer will come when I plug in numbers to here. So let's take this Q metal and put it in right here. C equals Q over M delta T. So Q of metal is negative 920.48 joules. And then on the bottom, the mass of the metal is 4.9 grams times, what's the delta T? Negative 487.9 degrees Celsius. So it looks like that. Notice we have a negative divided by a negative, so it will become a positive answer, and you should get a positive answer for the specific heat capacity. Once again, how does that look like when you calculate it on the calculator? Let's take negative 920.48 divided by 4.9 equals, divided by negative 487.9 equals, and we get that answer, equals 0.385023696 joule per gram degree Celsius, always have units, and that rounds with proper sig figs to, wait, how many? Remember, ignore temperatures for sig figs, but this is 2 sig figs, this is 3 sig figs, and the reference numbers we looked at from the table were 4 sig figs. So it looks like we are going to use this 2 sig fig number right here to determine a final answer of 0.39 joule per gram degree Celsius for the metal, which, FYI, that just happens to match copper, so it's probably copper. But it didn't ask that in the question, that's why I didn't bother writing that for an answer. All right, next one. How many joules of energy to raise the temperature of that many grams of water from that to that? Okay, this one, temperature changes, you know Q equals MC delta T is going to happen, but you notice this is the temperature of ice, this is the temperature of vapor. We're going to do multiple calculations. So essentially, what we're looking at is a situation where you're starting as ice, and then you're going to melt the ice, and then you're going to have liquid water. You're going to warm it all the way to 100 degrees. This is 0 degrees, by the way. 100 degrees Celsius. And then when you reach 100, it's going to plateau and stay at that same temperature until it's finished evaporating. And then the vapor will go all the way up to 250 degrees. So 1 calculation to warm the ice, 2 to melt the ice, 3 to warm the vapor, or warm the liquid water from 0 to 100, 4 to vaporize all the water, and then a 5th calculation to heat the vapor from 100 degrees where it starts to all the way up to 250 where it ends. So what's that look like? Oh boy, here we go. Warm it from negative 40 to 0. So that's calculation number 1. From negative 40 to 0. That's Q equals MC delta T, which equals the mass, 75.5 grams, times 4 point, sorry, wrong number. It's not liquid water. Specific heat capacity of ice is given as 2.11 joules per gram degree Celsius. 2.11 joules per gram degree Celsius times from negative 40 to 0. Use your brain. From negative 40 to 0, that's a 40 degree temperature change from negative 40 to 0. So times 40 degrees Celsius, because it's going up by 40 degrees. When you do that, you'll get that number, 6,372.2. So 6,372.2 joules, which we will round to, let's see, 3 sig figs. So 6,370 joules. All right, number 2, we're going to melt the ice. 75.5 grams times 334 joules per gram. Where did that number come from? Right here. Why did I do it that way? Because gram cancels gram to give joule for a unit. Melting the ice does not involve a temperature change. And that gives an answer of that many joules. So we'll round that to 3 sig figs, which is, well, let's see, 25,217 joules, which we will round to 25,200 joules. And now we have liquid water now that it finished melting. Liquid water is going to go from 0 to 100 degrees Celsius. So Q equals MC delta T again. And that means the mass of 75.5 grams times the 4.184 joules per gram degree Celsius, that's appropriate for liquid water, and that's multiplied by 100 degree temperature change as it goes from 0 to 100. and degrees Celsius cancels degrees Celsius, gram cancels gram, and you're going to get an answer of that. 31,589.2 joules, which will round for sig figs to 3 sig figs, 31,600 joules. All right, that calculation took us from 0 to 100 degrees. Now it's boiling water. Now to vaporize it. That number for vaporizing comes from here. So 75.5 grams times 2,260 joules per gram degree Celsius equals 170,630 joules, which I'll round for sig figs to 3 sig figs. So 170,000. What's 3 sig figs? Well, 171,000 joules for boiling it all the way from liquid to vapor. Now, fifth calculation, you're going to take that 100 degrees Celsius vapor and heat it to 250. So that's Q equals mc delta T, which is the mass of 75.5 grams, times the specific heat capacity of vapor, which is this, the 2.00 joules per gram degree Celsius, times the delta T value, which is you're going from 100 to 250, so that's 150 degrees Celsius temperature rise, and then you do that math, and you get that number. So that is 22,650 joules, which rounds to 22,000, let's see, 3 sig figs, okay, 22,700 joules. So, all right, that's done. Now that was all the way from negative 40 up to positive 250. Now I got to add them all together. 1, 2, 3, 4, 5 answers to add together. So stack them up, 6,370 joules. 25,200 joules, and then 31,600 joules, and then 171, oops, crossed the wrong bar, 171,000 joules, and then 22,700 joules. And then you got to add all that together. And that's your raw answer, 256,870. I need to line the numbers up properly. 256,870 joules. So underline the last sig fig in each number. This is the one furthest left, so we got to round at this location. This is pointing at the 6. So that's going to round to 257,000 joules. And let's put that in scientific notation the way it should be. So 257,000 joules becomes 2.57 times 10 to the 5th joules. That's the final answer. Let's talk about how we're going to do this one now. A reaction occurs inside a calorimeter containing that many grams of water, and the reaction causes the temperature of the water rise from that to that. Calculate Q for the reaction with units of calories. So aside from the fact that this is Q, this tells us there will be a delta T. So Q equals mc delta T is going to be happening here. So when we talk about a reaction to calorimeter, we got to understand it means that the reaction is surrounded by water, and the water's temperature rose, so the water must have absorbed energy. The reaction must have released energy to the water, so we're going to have to deal with that. But before we do that, let's note that we're going to be doing a delta T, so we might as well calculate our delta T now. Temperature increases, so we got to make it positive, so I'm going to subtract in this order. That way it's going to give a positive result. And when you do the calculation, it comes out to that number. So that's 3.2 degrees Celsius. So how are we going to deal with this? So if the temperature went up, it's because the water absorbed energy. We're going to note that if we want to calculate Q for the reaction, it's going to be the same number as Q for the water. So the water is absorbing all the energy that the reaction loses, or if the reaction were to gain energy, it would all be sucked out of the water. So they're going to have the same numerical value. That said, clearly water is gaining energy because its temperature went up, which means the reaction must be losing energy. So I'm going to put a negative sign here because the reaction must have lost energy, the water gained energy. So we're going to calculate the energy that the water gained and understand that it's the same number of joules or calories that the reaction lost. So let's calculate Q for water. Q equals mc delta T. So the mass of the water is 2,216 grams times the specific heat capacity of water. Very tempting to go for this one, which is so often used. However, it wants calories. So you got to make sure to do it for units of calorie. So it's 1.00 calories per gram degrees Celsius, and then the delta T of 3.2 degrees Celsius. Note that degrees Celsius cancels degrees Celsius, gram cancel gram. It will give calories as the answer. So if we plug that into the calculator, you'll get a number like that. So that is 7091.2. So 7,091.2 calories was absorbed by the water. Now let's round that and convert that to sig figs, so that looking at the numbers we used, ignore sig figs for temperature, 3 sig figs, 4 sig figs. So 3 sig figs it is. That is 7,090 calories, which we will round to 7.09 times 10 to the third calories for water. And since the water absorbed the many calories, we want to do Q for the reaction. If the water gained energy, it's because the reaction gave it energy, i.e. lost the same number of calories. So negative 7.09 times 10 to the third calories for the reaction. And that's the number that's getting boxed, and that's the number that's going to serve as the final result. There we have it.